okay with it. So the small changes as follows. Initially we said that the basically the reviewing of somebody else's homework only counted as 3%. So we are proposing to increase that percentage to 10% in exchange for one less homework. So basically the deal is either you get the 6th homework, or we leave it at 5 homeworks and we increase the percentage of the reviewing to 10%. Who votes for 5 homeworks and 10%? Okay. Who would rather have a 6th homework and 3%? I think this is the overwhelming majority. So yeah, so basically I think that was an easy decision, and I guess we also have a quorum, so okay. So by the way, I mean, there's obviously also the final projects where we'll still need to rely on you for reviewing, so don't worry, there's still plenty of time where you can do a good job. Okay, so the two things that we are going to cover today is we're going to wrap up the Archaeopteros paper, which has now been dragging on for at least one lecture, possibly a little bit longer. Basically, I gave you an advanced preview of what's going on in Monday last week. Then we really went through some of the math on Wednesday, and today we're going to wrap up the last part. So the key parts of it, and this is why I want to explain at least a little bit of how to get those results, and details are always found in the original paper, because there's just more content than what I can cover. So remember, we wanted to get something that gives us a good embedding. In other words, we wanted to have a mapping that maps vectors xi into some f of xi, and well, I'm actually going to, in this case, assume that it's some matrix, and let's just use v times xi, such that 1 minus epsilon, and then here we have vxi minus vxj squared, for instance, is less equal than xi minus xj squared is less equal than, well, 1 plus epsilon vxi minus vxj squared. And this has to hold for all I and j in this set going from 1 up to n. That was the key point that we started with. So first sanity check. Why is it okay to square things here? Well, basically, if I was to take a square root, right, the inequalities would still hold, except that I'd get the square root here, and then you just do a series expansion in epsilon, so you can always, up to second order terms, make the epsilons kind of match up. You might lose a factor of 2 anywhere, but that's fine. Now the second thing is, and this should also be quite familiar from last week. Well, if you have all those pairs, you get n choose 2 pairs. But since we typically then need to get the probabilistic bound for upper and lower, this is of course nothing else than n minus 1 times n. So basically it's a bit less than n squared. Okay, good. So first we had the subspace projections with rescaling. Then we had the Gaussian projections and the database-friendly projections, and this is the only reason why I'm going through them in a bit more detail, is because they introduce the fact that actually these matrices V don't have to be isotropic. all we have to be able to do is get good estimators of the length of x. And so what we did is we have basically Vj dot x, and again, since we have all those pairs, all we need to do is we just need to make sure that this condition here holds for a prototypical vector Vx norm squared less equal than norm of x squared less equal than 1 plus epsilon norm of Vx squared. And then we just invoke this n minus 1 times n times, one of those inequalities, and we're done. Okay. So the idea was to have the sum over all the j's, and after suitable rescaling, for instance, after rescaling it with d over k, that this would be a good estimator of the length. So in other words, yeah, these are the projections. And as we saw, this is, of course, nothing else than, okay, the expected value of this quantity is nothing else than x transposed, and here I have the expectation of Vj transposed x. So all I needed is that this be the identity matrix, and I'm safe. So the first thing that you would come to mind is you pick a Gaussian, and for a Gaussian this trivially holds, right? But I can of course also pick some other distributions, and the two that are a little bit more interesting are first of all the distribution plus minus 1, and then the distribution which has plus minus square root 3 and 0. So this occurring with probability 1/2, 1/2. This occurring with probability 1/6, 1/6, and this was 2/3 respectively. Okay. And essentially what I just want to go through again, because it looks like this might be a good idea to just repeat that proof strategy again, namely, you know, exponentiating things, optimizing over terms, because I found out this morning that maybe I didn't explain it quite as clearly as I should have, is to do this. So suppose I want to bound the probability that something like this holds. The probability that some f of x is less equal than some constant c. Okay. Or actually, let's make it larger than c, just because we want to bound large deviations. Otherwise, you have to switch things in your mind. Okay. So this is equal to the probability that, well, e to the t times f of x minus c, right, here is greater or equal than 1. And this holds for all t greater than 0. Right? So this is just really rewriting the definition. This should be utterly unsurprising because we did this twice already last week, which is of course less equal than the expected value of e to the t f of x greater than 1, yes. Yes, absolutely, otherwise it's nonsense. This times e to the minus tc, right? And then the nice thing happened if this f really happened to be a function of a sum of independent random variables. Let's say f is the sum over then you could actually work this out as e to the minus tc expected value for e to the t fi of xi, this entire thing raised to the power n. That's a general template. So this also is, for instance, what the method of exchangeable Stein pairs uses, except that rather than taking independent random variables, it's a little bit more clever in computing those expectations. Okay, so this is just a brief recap. Now, the interesting case in our setting is where, well, since this holds, so we know what the expected value is, right? And so now all we need to do is we need to show that the moment is actually well behaved. Now, I'm not going to go into details here. I'm just going to argue and explain in ideas, just the basic steps of how this proof works. So the first thing that the analysis in Achlioptas et al. Does is, because I mean our f of x, right, is just sum over I going from 1 to n, to k vi dot x squared. So these are the fi's, so to say. And so the argument is there, and you can verify that the largest variance, so the largest value in this expectation here, will be realized if the x's have all the same entries, but basically they sit on the vertices of an L infinity cube. In other words, it will be realized if the ith coordinate is in plus minus 1. So basically, the x's have to be one of those points. And actually, that's not that hard to see if you squint at this distribution here. It basically just means that you're going to have a lot more variance if the values are large here. Right? So that's essentially the idea of how you can get the largest variance for one of those vertices. So that's step one of the proof. And yeah, okay, basically look at the paper for that. I just want to quickly wrap this up. The second step is then to realize that actually these expectations here, so basically the expectation under e to the t, and then here we have v dot x squared, for v drawn from one of those Achlioptas distributions, for lack of a better word, are less equal than the corresponding quantities e to the t v x squared for x drawn from a normal distribution. And the way to show this is, at least this is how he shows it, is that this holds for each and every moment. I mean, we only have to look at the even moments because the odd ones go away. But basically, he then argues that this quantity is upper bounded by a Gaussian for each of the coefficients. And if this holds, then clearly this inequality holds for any linear function thereof, so we are safe. And this also shows that effectively these distributions, even though they look a lot more barbarian than a normal distribution, actually are better at estimating the length despite not having all this nice rotational invariance. And as a matter of fact, for most points they will be very nice. And here's actually an example for the worst case that can happen. So the reasoning basically goes, construct the worst vector. Show that all other vectors can be embedded at least as well as the worst vector. then show that for this worst vector, the Gaussian moments are better behaved than this guy. We need this worst vector because for this we can explicitly work out the moments. And once you have those two pieces, you're done. There's one tiny little extra bit, and that tiny little extra bit is that if you need to get this inequality, because we need to get an upper and a lower bound, right? For the upper bound, well, that's all fine. We just plug in the Gaussian moment. For the lower bound, actually what you can do is you can take a series expansion of this exponential. Since you have a lower bound, you have a minus in here, so you're getting an alternating series, right? And if you have an alternating series, well, you can truncate at any point suitable to the alternation if all the coefficients are getting smaller. So in other words, as long as you're within the right convergence radius and all the coefficients are monotonic. Bottom line being, you can basically truncate after the fourth order moment. He works out the coefficients for that explicitly, and that's it. So plugging those terms back in, because, see, the Gaussian case is actually worse than the case we're studying, you get at least as good guarantees as the Gaussian case, and that's what we did already before. So, wrapping it all up, any vector is worse than the vector with vertices on the unit cube, which is worse than the Gaussian for any vector, and then you just plug in the bounds for the Gaussian. That's that. So for probably a whole bunch of other distributions, you could work out some other interesting special cases, but this is probably one of the more fun settings to study. Any other questions about these projection arguments? So compressed sensing then would be to say, well, let's take those projected data points and let's go back to the original data. And there then the question is, you know, with what kind of V's can I get away with in order to get still a reasonable result? So I don't know whether there are currently good results if I have those Arcleopter style projections. I would expect that by now somebody would have solved this. Yuxiang, do you know any of such results? Because
depending on what you're looking for, but as long as your matrix satisfies certain conditions, which with large probability these matrices should satisfy. So
yes.
If they RIP, RT,
yes.
or the incoherence condition, then you are guaranteed to recover like the actual exact matrix from the subsample,
yes.
or to recover the underlying signal with only a subset of measurements.
Yep. Okay, so there you have it. Basically, you'd need to show that these projection vectors are sufficiently incoherent that you can prove this, and I think that would be actually quite feasible. So the game at the moment is to see how sparse such matrices you can also get away with. Basically, you want to do little work. You might have more interesting structures. So all of those pieces, they are basically the counterpart to what we studied. So we studied the high to low case. Compressed sensing does the low to high case. Okay. Now, this is all very nice, but I actually want to show you a couple of applications of this. So basically, let's solve linear systems of equations. So this is what we're going to have a lot of fun with today. So recall the prototype algorithm for, so this is now switching over to the Halko, Martinson, and Trop paper, which basically uses those projections to make high probability statements about what you can do with matrices. And so I'm assuming that I'm given some matrix M. This matrix M is in R M by N. And I want to make interesting statements about M. So one of them might be, for instance, what's the range of M? What are the singular values of M? So can I find lower dimensional approximations correspondingly for M. Can I do something special whenever M is Hermitian, or when even M is positive semi-definite? And it turns out that there are specific algorithms which will do that for us. And we're going to encounter some of them today. You may or may not have heard of the Nystrom method. That actually turns out to be a special case of this. And we'll derive it in maybe a slightly non-standard form. So the general prototype of the algorithm is going to be something of as follows. Step 1. Generate some test matrix omega. And this omega may very well have all Gaussian entries, but it may also be something that you can deal with a little bit faster. So in the arXiv preprint of the Halkamp-Martens-Netrop paper, there's actually somewhere when they discuss other matrices a typo where they basically have a dependence that is logarithmic in n. And it actually turns out that it's logarithmic in the number of dimensions that you're testing for. So this is, yeah, basically they seem to have copied some reference across not perfectly correctly. So this reference is, amongst other things, something called a subsampled random Fourier transform, SRFT. And the idea there is essentially that Fourier transform matrices are, if I pick out random rows, are essentially behave like random matrices. And so under certain conditions, and by being a little bit more clever about how I design them, I can actually get something that's very similar to what we discussed in fast food, which isn't so surprising because that's basically how we started with fast food. Basically, you can treat those matrices as a proxy for devices by which you can multiply in less than the usual cubic time. Okay. Any questions so far? Okay. Good. So you first generate this test matrix. You may actually only want to generate it implicitly, and I'll talk about that in a moment. You then compute A equals m times omega. Then you typically do something smart to A. For instance, you could compute a QR factorization. Okay. So just, to give you a bit of an intuition about the sizes, this is maybe some gigantic matrix, m by n. You want to make it smaller, so you generate an n by k matrix. Okay, this is n, this is k. And so you end up with this matrix A, which is now m by k. And then you go and compute A equals Q times R, where Q is a matrix with orthogonal columns. Okay. Actually, that's all I need. I don't drew this wrongly. Q times R. And so now this allows me to have a good guesstimate. This is my Q matrix, this is R. This allows me to come up with a good guesstimate of what the image space of M is. Okay. So here's a question. Why can't I just go and say, well, you know, I'm going to compute the inner product between omega and M, maybe left and right with some random matrices, and then, you know, just maybe, you know, use omega to pick some some basis system. Why is this not a good idea? So why do I actually need to multiply this random test matrix omega by M to say anything meaningful about the matrix?
I think we're interested in the matrix.
We are interested in the behavior of M, yes. But why can't I just say, well, I'm going to project the behavior of M onto some random set of, you know, test vectors, just like what I did before in compressed sensing, and I use that to make statements about M, and everything's good. Why is this not good enough? What could possibly go wrong? Or rather, what will go wrong if I do this? Well, so remember the rank of this matrix omega is fairly low. So, you know, it's k-dimensional subspace. And almost certainly the image of M is going to be very different from this small k-dimensional subspace that omega would have picked. It's going to be vastly different. It could be, you know, entirely orthogonal to it. It might not be really orthogonal, but it's going to be vastly different. So now that means that I can use omega to find out what the typical behavior of M is, I actually need to look at the image of under M to make any statement about what M behaves like. So there is plenty of information about the image space that I can only elicit from M by actually applying M to some test. Otherwise, I won't get it. So, for instance, it could be that the image of M are like the first 10 dimensions, right? So in other words, it has rank 10, and that's it. But if my test matrix omega was just a generic Gaussian matrix, it would have things, non-zero things happening in all dimensions. And I would actually start fantasizing a substantial part of an image space that doesn't really exist. And that could actually make the approximation really, really lousy. That's why I need to form the product between M and omega rather than just saying, well, let me just expand into those basis functions. Yep?
But the Johnson industrial lemma tells you, like, project it onto k dimension with k large enough, you have pairwise distance reserved, and like, that's the only guarantee it gives you, that still holds.
Exactly. So that still holds. So if I'm happy to replace the action of M by the action of some other matrix that is related to M by a rotation, but except that I don't know what that rotation is, then I can get away with not even having to guess it. But typically, I will actually care about the subspace in which M acts, so that's why I need to multiply M by omega. So that's the intuition behind that. Okay. Does this help a little bit with why on earth we actually need those test matrices? Okay. So so once I have this Q, which now tells me exactly what that image space is, I can go and reapply to M, because this is now a pretty high quality guesstimate of that space. And then do something like, well, analyze B is Q transposed M, and maybe perform an SVD or something of that form, which now is a K by N matrix. So in other words, I throw R away and just keep Q. And now you can maybe perform an SVD on that. And we'll look at the various details in a moment. Yep?
Why do you take the Q out of A? Why can't you just take the Q out of omega?
That's exactly the point, right? So if I did the QR factorization of omega, or in other words, I could just go and actually pick a random subspace, right? Because that's all I would really get if I took the QR factorization of omega. As a matter of fact, this is what the Dasgupta and Gupta paper suggests. You know, generate some random subspace, do stuff there. So that, with high probability, would not give me any subspace that would be terribly well aligned with a subspace in which M really acts. And if I need to approximate the action of M on anything, right, then I actually need to know the space on which it acts. That's the idea.
So like when you choose when your random matrix is actually M dependent, like do these guarantees take hold?
Well, no, I mean these guarantees. So for this type of work, there are actually fairly strong guarantees, and they are typically of the form that you're going to do almost as well as if you performed an SVD on the full matrix. So the type of approximations that we might be after, for instance, is something of this form. I want to minimize the discrepancy between M and its projection onto some k-dimensional subspace given by Q transposed M. Right. So we all know what the minimize over Q with a rank Q is K. We all know what the answer of this is, right? This is? Well, so what do I need to write here? Sigma, now what's the index? Exactly. This is sigma K plus 1. And the theorems will be of the following form. Let me just pull up the details because there is a fair number of those. So, for instance, if I oversample by a factor of by 2, in other words, if I go and add 2 extra dimensions, then I can show that actually for this type of method, I'll get is in expectation over this, over those Q matrices is less equal than 1 plus 4 square root K plus P over P minus 1 min of M and N square root sigma K plus 1, which doesn't sound too amazing, except that it actually is pretty good, given that otherwise you would have had to check out the entire matrix. And there are corresponding statements that hold with high probability. Furthermore, whenever those singular values decay rapidly enough, you can actually get statements that don't really depend on the dimensionality of the system anymore. So P is basically the number of extra dimensions that you're using. So in other words, rather than, for instance, solving the problem, well, find me the best 10-dimensional subspace, I'm going to give you a 12-dimensional subspace back. And the claim of this result is that in expectation, this 12-dimensional subspace is going to be almost as good as the best 10-dimensional subspace. So I'm going to make the problem a little bit easier. And I'm going to show that that the solution to the slightly easier problem is, in expectation, going to be almost as good as the optimal solution to this lower dimensional problem. So basically, I'm weakening things in two ways. I'm relaxing the dimensionality constraint a bit, and I'm also relaxing, well, the optimality. But then I can get guarantees, nonetheless. So there are various results about how hard or easy it is to find those things in various cases. I don't think we want to go through this in like a crazy amount of detail, but the idea is essentially you can get that type of statements and our probabilistic statements, and if you have different rates, you can get slightly more refined results for all of this.
And this holds for all p, right?
This holds for all p greater or equal than 2. Well, for p equals 1, this is undefined, right? You get division by 0.
What happens when you use p equals 1 is there?
Well, then that guarantee doesn't hold. There may be some guarantees that you can still get for p equals 1, but why would you bother, right? You're extracting 100 dimensions. What's an extra 2 dimensions between friends? So you would typically expect that the randomized algorithm isn't as good as the optimal thing. So it's perfectly okay if you maybe perform 5% extra work in exchange for something that's basically as good as the thing that you would have done otherwise.
This means that you need like at least a constant of m or n. You need p to be equals 0.
If you did this, yes. So if you did this, I mean, so the dimensionality here enters only via the square root. Well, let's say we pick p equals k, right? So this basically gives me something like square root m over p, right? Which isn't too bad. Also considering that these singular values may decay quite rapidly. So, if those singular values, for instance, like in a kernel matrix, decay exponentially for a Gaussian RBF kernel, then adding 2, 3 singular values pretty much takes care of things. So for a lot of real data, you've probably done PCA for a lot of data, and you would have noticed that the eigenvalues decay very rapidly. And this is also what saves you. So that's part of the reason why these algorithms are actually really good in practice. I mean, their case in point was to actually solve a linear system by streaming things in from from hard disk, from a slow disk. Okay. Now let's go back to this rangefinder. So the idea is basically, well, it actually stops here. And so then let's just look at the computational cost. And let me quickly talk about why you would not necessarily have to store omega, but why it might actually be in your interest. So suppose the omega ij's are drawn from a normal distribution with zero mean and unit variance, right? So then, well, you could go and look things up in memory. That's fine. And if this matrix is big, it'll cost you a lot. You could also do the following thing. I could basically, at each time, regenerate these draws from a normal distribution. Now, that may be a little bit awkward, except that actually it isn't. Let me show you. So the naive way of doing this is, of course, I take the inverse of the cumulative distribution function of hash of I and j divided by basically n max. Right? So if I do this, I will get something that effectively behaves like Gaussian. Now, unfortunately, this turns out to be really awkward to solve. What you can do instead is use the Box-Müller transform, which I think we covered already in the past. Okay. Who remembers the Box-Müller transform? Ina does, Shashank does, Mu does. Okay, well, let me quickly refresh the idea. So the only slightly iffy bit about the Box-Müller transform is it's very cheap to get 2 Gaussians from 2 uniform random variables rather than 1 from 1. And effectively, here's what happens. If I have a Gaussian in 2 dimensions, right? So I get that P of, r and phi in polar coordinates is basically the uniform distribution 1 over 2 pi. So this takes care of the phi dependence. And I'm just going to write it as proportional because this is very easy. And then I have r times e to the minus 1/2 r squared. So now all I have to do in order to get Gaussian random variables, I basically have to solve this integral, which is fine because that's the derivative, the stem function of that is e to the minus half r squared. And so all I have to do is just compute the log of one random variable, the square root of that, and that will give me the radius. And then sine and cosine of the other one, that will give me the angle. So in other words, we'll get cosine of 2 pi psi 1 times square root, and I think I may have forgotten a factor of 2 somewhere, and I have here log of psi 1. And here we have the sine of the same thing. And so, if I have to compute this for adjacent i's and ij pairs, let's say ij and ij plus 1, I can actually, instead of doing a memory lookup, perform cosine, sine, and log, and I get the same result. This can be faster, and in some cases it may actually fit in memory, whereas the other one doesn't. Okay, this is called the Box-Müller transform. Okay, and I think there's a Wikipedia page on that. Okay, so now back to this. Well, that's all very nice if I have those theoretical guarantees. What would be just so much nicer is if I actually had empirical guarantees that I could just invoke. Because, the theoretical guarantees are as good as your theorems are. The empirical guarantees are as good as what reality is. So it's always going to beat the theorems. And it will also tell me if I just so happen to get unlucky. Okay, and we briefly actually touched upon this on last Wednesday, namely when I said, well, here's a way how to get the norm of a matrix. Remember that with high probability, the norm of the matrix was going to be less than alpha times square root 2 over pi. And here I have the max of the norms of m times omega I over I with probability 1 minus alpha to the minus k. So I less equal than k. So does everybody remember how this bound came about? Okay, well, let's take a Gaussian. So first of all, it's easy to see that this majorizes the distribution that I get by taking inner products between W and the largest of all singular values. Right. So we have basically a sum over squared Gaussian random variables, and we threw everything away but the largest term, so this is therefore going to be majorizing the Gaussian. Now, if you squint hard at the Gaussian, you can see that at its largest value, Gaussian with zero mean and unit variance, is going to be bounded by 1 over square root 2 pi. So now, if I go out by an extent of 1 over alpha, right, then that area here is going to be 2 times 1 over square root 2 pi, so we get our square root 2 pi times 1 over alpha. Right. And then by, actually I should have called this thing here beta, 1 over beta. And then by using the fact that for Gaussians that have, not unit variance, you need to rescale everything, right? And you divide things out, you get exactly this guarantee for a single random variable. Because what we need to do is we need to upper bound the probability that something happens here inside this box. And of course, the value of this integral is upper bounded by the largest value inside the box times the width of the box. This is about the most primitive bound that I can make. So this is the opposite of a tail bound. Here I want to upper bound the probability of ending on the head rather than the tail. So this is this is a head bound, right? And for that head bound we get that the width of this actually matters. And the width tells me, so basically if I end up outside here, I'm going to get a large enough value, because these are exactly the cases I want to avoid. I want to avoid the situation that my projection happens to be very small. So I want to avoid being unlucky. Right? So that's how the argument goes. Now, if you take a step back, you look at those omega i's. Well, these are exactly the columns of my test matrix omega. Right. So what this in turn does is it means if I apply this to my matrix, right, I get immediately not just an estimate of the range, but I'll also get an estimate of the norm of the matrix. It might be a really horribly lousy upper bound, but it's going to be an upper bound nonetheless. Okay, so what do I do then? I then go and perform this approximation. Okay, so I get some Q matrix out of it. And then, in the next step, I define M prime to be M minus Q transpose M. Okay. And now I can say, well, hey, let me now try to find out what a good subspace approximation of this would be. So this is my residual. I'm now going to find out what the norm is for the residual. I again use some other matrix omega prime. I then, first of all, get these bounds that I have on top. And secondly, if those bounds are too large, it means I have to keep on approximating further. So I actually construct a bit more of a subspace. So then I add to my original Qs, the Q primes, maybe Q2 primes and so on, and I keep on going until I've approximated the matrix well enough. So in other words, I'm never really doing something that's wasteful, because I'm basically going to reuse the same quantities for estimating the norm of the residual and approximating the matrix better, which is kind of a useful thing to do. Okay. Now, you might obviously still think, well, that's a little bit wasteful, right? Because, well, in the last step, let's say, I'm picking k being 64 or something, I might have wasted 63 out of those 64 steps. Well, fear not, you can actually make k equals 1, and you now go and add one subspace at a time. Okay. Now, last question. Why can I just go and have q goes into q and q prime? Why can I do this? Any suggestions? Why is this okay? Because, if you think about it, this is actually weird, right? Why can I just, take the residual, multiply by some other Gaussian random matrix, just paste those orthogonal matrices together and hope that nothing will go wrong? What prevents disaster? Any idea? Okay. So let's look at what happens, right? Sorry. Yes.
Multiply by Q transpose, it will be 0. So
exactly.
That means the Q dash will be independent of Q.
Will be orthogonal to Q. Yes. That's exactly the answer. Because what happens here is that this is a projector, right? I can write it as 1 minus Q transposed M. This is a projector into the orthogonal space to Q. So therefore, any further vectors that I extract from the image of this new matrix M prime now have to be orthogonal to Q. And given that they are orthogonal, well, a QR factorization of that new subspace isn't going to change. And that's all it is. Now, this also means that I can, for instance, do the following thing if I was to compute one vector at a time. I would go and compute basically something like AI being AI minus Q. Okay, first of all, I compute AI equals M times omega I. Then I project out things by computing AI minus Q transposed AI. Now this vector here is what will go into this bound up there. Because this is the residual. This is the residual at the beginning of step I. And then, because this is orthogonal to the Q's, okay? So now all I have to do is just renormalize this. So I get that Q goes into the vector q, and then I get ai divided by the norm of ai. Because this is now clearly orthogonal to q, because I've projected out anything in the subspace of the q's, so I've added another dimension. I'm basically building up a subspace one step at a time. The only thing that you would have to pay is theoretically slightly weaker guarantee, because you're essentially applying, it's essentially multiple testing. You're testing after each projection whether things are okay. So that's multiple testing. This could, worst case, cost you log number of steps. But that's actually overly severe, because you're multiply testing with dependent random variables, and you're guaranteed that the norm of the object keeps decreasing. So in practice, you can probably safely ignore this. Working this out in detail would be probably a fair amount of work. Okay, but the other thing, and this is where the Halko, Martins, and Trop paper becomes a little bit cryptic, is, well, this can give you algorithms that are not amazingly stable. And so they suggest some explicit normalization, but actually, if you read through the explicit normalization, they just do that anyway. So it's very hard to understand what's different between their simple and their supposedly numerically stable algorithm, because they're identical. Okay. Good. So this is the rangefinder. I don't know whether they intended it as a pun or not, but it's also the name for a type of cameras. Okay. Any questions about this? Okay. Now, so a couple of things that can go wrong if the singular values in M don't decay very rapidly. Because, well, if you look at this, if I don't really pick the right subspace, I might just end up projecting on too much. Well, you could argue if the singular values don't decay very rapidly, probably a low rank approximation is going to be a poor idea anyway, which I would tend to agree. On the other hand, if somebody tells you you must find a low rank approximation, well, okay, here's how you can make it better. So let's say sigma I decay slowly. How can I make them decay faster? Any suggestions? Right? I mean, they are what they are. But what can you do to make them go faster? Exactly. So you apply the trick several times. This is exactly what the power method would do. So instead of dealing with M, I'm going to deal with M times, and now here I have M transposed M raised to the power Q. Okay. So this now will have a behavior in those singular values that goes like 2Q plus 1. Okay. So this is much better. Few questions. What could possibly go wrong if I was to use this?
How do you plan to use this? How do you, for instance, compute?
Okay, so what I'm going to do is, instead of taking m times omega, I'm going to do this. And then I'm going to perform a QR factorization just as before. So I'm going to replace step number 2 by this.
My question is, how do you compute A? Do you actually compute this matrix?
Yeah, well, okay, so first of all, you would never explicitly form this. This would be fatal, right? Because if this is, a million by a billion matrix, right, you don't want to be messing around with a billion dimensional matrix. I mean, this would make things a lot worse if you explicitly formed it. However, okay, so the first question is, how do you actually evaluate this? Well, what you do is you first apply omega to M. You get something out of it. You then apply to M transposed. You get something out of it. Then again to M. And you keep on doing this Q times. So therefore, the first obviously bad thing is, well, this is, 2Q plus 1 times as expensive as the simple thing. What it does is it amplifies the decay in the spectrum. And this amplification, if let's say you pick Q equals 2 or Q equals 1, I mean, that gives you the third power of the singular values. That can actually be much faster than the singular value themselves. So this can do a lot of good. But there's a couple of other issues that could go wrong. And the first immediate issue is that, well, if you were to do this, then, well, you can run into numerical instabilities. Because what now happens is that the errors that I have numerically also end up blowing up. And so if before that I had an error of size epsilon, afterwards I can only tolerate an error of the size 2Q plus 1. Right? So that means you pretty much need to use double precision, for instance. So this is if you do this naively. Now there are ways around that problem again, right? Because part of that problem is that, if now some of the eigenvalues get really large, things are bad. So what you can do is you basically perform a QR factorization of this. Then you take that Q matrix multiplied with M transposed. You get another QR factorization, get the subspace again, and you keep on doing this. This is, of course, way more costly because now you have to perform a QR factorization at every step. And which of those things you pick in particular are very much a function of what kind of result you want within which computational and memory constraint and which accuracy constraint. So for machine learning, we probably might not bother with this. Unless, for instance, I have some large graph Laplacian and M is, of an interesting form, and I want to get a good low rank approximation. So this might be interesting also because it might give me a good idea of what the residual null space is and all sorts of other properties. So for large graphs, this may actually be a good thing to do. In general, yeah, for numerical analysis, you would care. In general, for machine learning, don't bother. But it's a useful technique to be aware of. Similar things are, for instance, what people do in spectral methods when they use like a tensor power method. And yeah, Fish is going to talk about that on Thursday in the reading group, amongst other things. Okay. Any questions about this so far? Everybody's very quiet.
I'm not sure if I missed it, but I just want to go back to that.
Yes? Okay.
I still don't understand why taking the QR of A would be helpful, because QR doesn't necessarily preserve anything about the spectrum.
What QR will do is it will perfectly preserve the image of A. So basically, what this will do is it will perfectly, this is exact. So therefore, Q perfectly preserves the span of A, which means it's a perfect approximation of whatever happened to omega once it was fed through M. So this is why this is going to be a good approximation of the image of M. So if, for instance, you wanted to have a better estimate for instance, low rank projections and so on, where you actually cared about finding a lower dimensional subspace that looked very much similar to the original data, this would be it. As a matter of fact, this is what you do in PCA, right? So when you run PCA, you get the singular value decomposition of your data, and then you project your data on the leading singular values or principal components.
Right. But in that case, like the leading components, they preserve the large eigenvalues.
Not just that, they also preserve what the data looked like. So for instance, if you think about eigenfaces, right? So eigenfaces, if you haven't heard of it yet, it's basically, this is like an ancient paper, I forgot the authors, but just Google for eigenfaces and you'll find it. Well, they went around with a camera, took pictures of people, and they ran PCA on those faces. Properly registered, calibrated, lighting corrected, and so on. So totally unrealistic assumptions, but anyway, okay, so they did this. And then what they found out is that, there's obviously the mean face, right, which actually is quite nice. And then you have variations in terms of, I forgot exactly, I think whether somebody has glasses or not would have been one of the first variations, or whether you have short or long hair and other aspects. And so you could, with sufficient amounts of fantasy, read something meaningful into those principal components. And since this was the first application of PCA to faces in computer vision, this paper got a monstrous number of citations. Okay. Doesn't seem so deep in hindsight, but a lot of things aren't so deep in hindsight. Now, what happens in this case is you're approximately preserving the data. Right? So what you're getting is basically then that a couple of dozen of those coefficients approximately will allow you to reconstruct something that looks like you or me or anybody else in this room, which is kind of surprising that you can get away with such a small number of numbers. If I just wanted to preserve the similarity, let's say, between both of our faces, I wouldn't care about reconstructing something that a third party can recognize as, being a picture of me. But instead, I would only want, let's say 5 numbers, which then a computer can compare and say, well, the numbers are similar, so therefore, the pictures are similar. So that's the big difference. That in one case, you care just about the coefficients. In the other case, you care about all the data. Or maybe in other words, in one case, you care about the projections onto the principal components. And in the other case, you care about the actual eigenvectors. That would be probably the closest approximation. Thanks for asking the question. Any other questions? Okay, good. So then, actually, we're almost done with this. Basically, what you do is you iterate, applying, normalizing. This, well, will do something interesting. At some point, you're going to get other numerical issues about, maybe not getting the right subspace, but overall, this is fairly effective. As a matter of fact, in the power method, people use this if they want to find the largest eigenvector-eigenvalue pair. You just apply the matrix to a vector, renormalize, and push it through again. Right? This is essentially just doing it for subspaces. Okay. Now, the obvious question is, do we really have to pick a Gaussian? And actually, it turns out there's a couple of other things that you could do. So the subsample random Fourier transform would do. The fast food matrices that we discussed a couple of weeks ago would do. In other words, if you have matrices of the form binary, Hadamard, permutation, Gaussian diagonal, another Hadamard, and then, well, basically a scaling matrix ad libitum. So this is basically the fast food construction. This is Charlotte et al. You can use the SRFT, or you can use something that looks similar to this but uses what's called given rotations. And I don't think the particular construction here is terribly instructive. What they also have is they basically have a Fourier transform matrix, some random scaling, and then in addition to that, they have two-dimensional rotations. So those things are called Givens rotations. And if you've never seen them, here's what they look like. Let's say I want to rotate between the first two dimensions. What I then get is I get cosine phi, sine phi minus sine phi, and cosine, phi. And then here I have 1 and 1. And this is a rotation matrix. And it'll basically rotate between the first two dimensions. You can see this easily by multiplying it by its transpose. You're done. And yeah, that's about that. And you basically pick arbitrary pairs of dimensions and you rotate between them. So there's plenty of other variants. For most of them, the theory is quite shaky in terms of proving that all the analysis that works for the Gaussians actually goes through. In practice, you'd be crazy to use a Gaussian. It's much cheaper. Okay, good. So now, let me conclude with what you can actually do with this. So the obvious thing is once you have that subspace, well, you can run an SVD. And this was already the algorithm template that I showed here, right? Basically, you have this matrix Q transposed M. So let's just go through the 3 steps. A is M omega. A is, Q times R. So in this case, I get some matrix B is Q transposed M, which is now U dV, and from which it follows that basically M is approximately given by Q times U times D times V, and since I'm multiplying two matrices which have orthogonal columns, everything is good, so this is another orthogonal matrix. So it doesn't have full rank, but the columns are orthonormal. Okay, and this is an approximate SVD. Okay, so this is actually a very, very simple thing that you can do. Now, one of the nice things is that all the error that I paid to approximate, the range of M is all I have to pay in order to get the approximation in M. Because, well, if I can rotate away that eigenspace, then everything else is kind of straightforward. Okay. Now, the next thing is, of course, what happens if M is Hermitian? Okay. So in other words, if M is M star, so it's transposing complex conjugate. In this case, what I can actually do is I can form Q transposed M Q. We call this thing here C. And then I just compute a vector eigenvalue decomposition. So this is just V transposed lambda V. And then I get from this that M is approximately, right, now we need to multiply by Q and by Q transposed, Q times V transposed lambda v q transpose. Okay. There you go. It's actually okay, good. So now the obvious question is, how good is that approximation? It's clearly not quite as good as doing the original thing, because I've now projected from left and right. So here's a simple inequality. It's kind of cute. It's so simple. So the norm of M minus Q transposed M Q transposed Q is less equal than norm of M minus Q transposed M plus norm of Q transposed M minus Q transposed M Q transposed Q. Okay, that's just a triangle inequality. Okay, this guy we know is less equal than epsilon. This we can rewrite, because this is basically 1 minus Q transposed. So this is basically a projector times. Now here we have M minus M Q transposed Q. Right? And now good things happen, because this is a projector, so the norm of this is less equal than 1. Right? And then furthermore, this quantity here, because I can just apply the norm to each of those factors, is less equal than epsilon. Because this is Hermitian, so I can just transpose it over, so that's fine. So I basically get that the entire thing is less equal than 2 epsilon. And I'm done. Now, this is very convenient, because it basically means that at the cost of only paying a factor of 2, I get the matrix approximation for Hermitian matrices a lot more cheaply. Now, the one thing that we're really interested in are kernels. And so here's a little thought experiment for you guys, because I think we need to finish now, and I'll tell you the solution on Wednesday. Suppose I have positive semi-definite matrices. How could I approximate M by some small matrix MK? Can you do this? And if so, what's the equation? And then the next step would be, can I do something where this is not just a matrix where I pick some subset of coefficients, but where I pick a subspace? And this is then the generalization of the Nystrom approximation. We'll get to that on Wednesday. Until then, I would say, well, good luck with your projects. I hope your projects are coming along well, because at some point there will be a report due. And somebody will have to review the report, and that's you. And then Yuxiang and Ina will play area chairs. Okay. Any questions? Okay, good. And thanks for that, and see you on Wednesday.